Welcome, ladies and gentlemen. Let's go ahead and take a look at our Bellwork today. We're going to translate a written description for a differential equation into the mathematical statement. So here we've got an above ground pool that's being filled with a garden hose at a constant rate of 7.5 gallons per minute. Ben knows that theoretically water should drain at a rate proportional to the square root of the amount of water in the pool. And so here we have to combine sort of this positive contribution that's trying to fill up the pool, increase the volume, right? So that would be a rate of change in the volume that's a positive contribution from the garden hose, and then decreasing by that drain rate that Ben does when he opens up that stopcock, and now the volume of the pool is trying to decrease as a result of opening up that drain. So let's put it together and write a differential equation that gives the instantaneous rate of change in the volume V of water in the pool with respect to time. Use K for the constant of proportionality, which we don't know. We weren't given data points, so we wouldn't necessarily be able to find K in this situation. And yet we can still get the family of solution curves and so on by considering my potential solutions for the differential equation. So let's go ahead and take a look. The rate of change in the volume with respect to time. What would that look like with Leibniz notation? Right, what letters would we use for that? Hayden? dV/dt. Good. I'll even use blue for our water in the pool. So dV/dt, thank you. And we've got sort of this positive contribution. This positive contribution, that's going to be our green light, right? Increasing. So we've got this positive contribution. And Mr. Fritz is filling the above ground pool at a constant rate of 7.5 gallons per minute. I saw lots of people had 7.5 T, right? Think about what 7.5 T would yield. Well, in context of this situation, if I knew how long I filled the pool for, 7.5, that expression when evaluated could tell me how much water had been added, yes? And yet the rate itself, it even says, is a constant rate. So we just need the constant part of that, 7.5, and that would be positive. So my positive contribution is a constant 7.5 gallons per minute, where T is measured in minutes, and so that's my 7.5 straight up. No T, right? If I had a T there, the rate of change, the positive contribution, would not be constant. It would change. It would be getting quicker and quicker. After 1 minute, it would be filling at 7.5 gallons per minute, but after 2 minutes, it now would be filling faster, right? At 15 gallons per minute. And so if it's constant, that means there's no variable in the expression, it's just the constant. Does that make sense? Minus this negative contribution. The negative contributions from Ben, tricky little rascal, he's draining the pool while I'm trying to fill it up. So we've got this negative contribution, we'll do that in red, and that was proportional to the square root of the amount of water. The amount of water here is going to be straight up feet, right? Not dV/dt, that's the rate of change in the volume of water, but rather the volume itself. And so let's see, proportional to means K times the square root of the amount of water in the pool would be the square root of volume V. And so we put it all together, we've got our positive contribution minus our negative contribution, K root V. Awesome. Raise your hand if you got this. Anybody get that? Yay, we got a couple. We got a sprinkling, right? We've got, that's when you get the bulbs, right? The bulbs for the tulips, and it's called naturalizing in your yard, where you just kind of do the Buford, the baseball birthday bunny, and throw them out there where they land there. Now, naturalize in your yard as opposed to measuring out with a little string in the stakes and putting them evenly across. All right, let's go ahead and take care of our OTL number 4. I did ask that you staple the half sheet on there. Okay, so if you kindly staple the half sheet on there. I'm going to pause the recording while we do this. Try and shorten up those recordings a little bit. Okay, ladies and gentlemen. So today we're going to investigate a different kind of model for population growth. We began the unit with investigating exponential models, and exponential models are appropriate to use oftentimes to model population growth in the early stages. Real-world data suggests that an exponential model would be appropriate anytime the rate of change in a given quantity depends on the amount of that quantity. If there's more bacteria in a petri dish, there's more bacteria to multiply, and the rate of change in the population will increase as the number of individuals in that population increases. But what happens as time goes on? as time goes on, are the bacteria going to continue to multiply more and more and more and more and more? Well, you're going to run out of alum, right? You're going to run out of resources. You're going to run out of space. If you put it more in a real-world context with the rabbits, right? You're going to run out of grass for the little rabbits to eat. The wolves are going to come in, and the wolves are going to, let's just say, modulate the rabbit population without getting too graphic, okay? And so in the real world, right, we're not going to have unrestricted exponential growth forever. There's going to be some limiting factor, and today we're going to investigate logistic models as an alternative, right, anytime we have this limited growth. So that's where we're headed today. We've got stamped eligible items at 3E, 5C, 8C, and wait for the fun images, right, as we come back together and have our closure discussion. We'll get a first look at some of Mr. Fritz's friends. I grew up in Cave Creek, Arizona, just north of Scottsdale, Arizona, and Phoenix, Arizona. And I went to all my high school down there. And so I've got some desert friends that I'm going to share with you after our activity. All right, I'll pause the recording. Let's scooch into our groups. Okay, ladies and gentlemen, so let's go ahead and take a look at our Roadrunner. So raise your hand if you've seen a Roadrunner in real life. Have you seen a Roadrunner in real life? Hey, buddy. Hayden texted me early this morning just to make sure that we coordinate our outfits. So we've got our close to Vans authentic and khaki pants. What are you gonna do? So here we have a nice picture of a Roadrunner. We're seeing it in the flesh, and we've got our equation where we could find, right? We could find what P equaled, and that involved a nice set of algebraic tools to do so. Actually, you guys did very well on that, so we're not going to have to go through. But I do want you to direct your attention to closure. So please be ready to share with the whole class. In what real life situations might an exponential model be appropriate? In what real life situations might a logistic model be more appropriate? How does the model's carrying capacity appear on the graph? And lastly, how many asymptotes does each model have? So how many asymptotes does an exponential model have versus how many asymptotes does a logistic model have? I went ahead and made a little bit more room so we can share responses on the whiteboard, and be ready to share your answer with the class when I call on you. Okay, ladies and gentlemen, let's go ahead and share responses for our closure exercises today. Thank you in advance for sharing your response with the whole class when I call on you. So in what real-life situations might an exponential model be appropriate? Riley F. Cursive? Yeah, anytime we have unrestricted growth, then an exponential model is going to be appropriate. So unrestricted growth might be the early stages of population growth. So certainly the early stages of population growth. When we would have to run into any sort of limitations on resources or space. So certainly unrestricted growth. Other real world situations where an exponential model would be appropriate. What about in the archaeologist column?
Determining money and savings account.
Absolutely, right? We use exponential models if we're doing our continuously compounding interest. And so continuously compounding interest would be another situation. Our APERT formula. And just because it's exponential doesn't mean that it has to be exponential growth, right? What other real-world situations involve exponential models? Kyle?
Carbon dating.
Carbon dating, right? So the archaeologist digs up the fossil, right, and to get an idea of how old that specimen is, you can compare the amount of C14 radioactive carbon in the specimen with the ambient environment and determine its age. And they're getting better and better, right, down to oftentimes a few hundred years, which is pretty awesome. So exponential decay. So that would be things like carbon dating. Any sort of those radioactive half-life type problems. Half-life, imagining dragons. I'm not gonna write that, I'm just saying it. Okay, thanks, that's a lot, and there's more. In what real-life situations might a logistic model be more appropriate? And so in what real-world situations might logistic models be more appropriate, right? Tyler?
Bacteria and petri dish.
Certainly, when we have a restriction then, so the bacteria are going to run out of space, they're going to run out of resources, they're going to run out of food, right, to grow. And so anytime we have limited growth, then that's a situation where we might consider a logistic model as more appropriate. Some sort of carrying capacity, a restriction. Awesome. How does a model's carrying capacity appear on the graph? Right? Well, how would that show up on the graph? Kobe?
A horizontal asymptote.
Absolutely. A horizontal asymptote represents that population's carrying capacity. We've got that leveling off feature for the solution curves. They're kind of leveling off as they near that carrying capacity. And how many asymptotes does each model have? How many asymptotes does an exponential model have? Kyle?
One.
One is correct. There's one asymptote. And I saw some of you had zero. Consider an exponential model. It does have a horizontal asymptote, right? An exponential model has a horizontal asymptote. As you look to the far left-hand side in the case of growth, there's that leveling off. All right, y approaches 0 as x approaches negative infinity, and then flipped if you're doing decay. And then logistic, how many horizontal asymptotes does a logistic model have? Sophia? Let's consider the graph of our roadrunner, our roadrunner population, right? How many asymptotes do we have? Well, if I did a quick sketch here, we saw when we got the ball rolling, it looked just like our exponential function, but then we had some limiting factor to our growth, and so it turns out that we have not one but two asymptotes when dealing with a logistic model. So two asymptotes. Awesome job. What questions do you guys have about your closure today? Great work, and you've got a nice chunk of time. You may work together. I'm going to go ahead and save the recording and upload it to our Moodle site.